All right, so my name's Josh. I'm a PhD student at MIT. If you're reading through my bio, I study atmospheric chemistry, so things like smog formation. But today I'm going to be discussing geoengineering with you all, which is a climate change solution that a lot of people are thinking about, but the implications of which are very uncertain and potentially incredibly risky and catastrophic. So let's begin first by getting all on the same page and defining what geoengineering actually is. And that is the deliberate manipulation of an environmental process that affects Earth's climate in an attempt to counteract global warming. So whereas climate change is unintentional, geoengineering is very much on purpose, all right? So think of it as the anti-climate change, if you will. Now, just to orient ourselves for the rest of the talk, I'm first going to be discussing climate change and the greenhouse effect in very broad terms, just so that we all have some background. And then we'll be going into geoengineering solutions, in quotes, for good reason. We'll talk about two of them today, carbon capture and sequestration and stratospheric aerosol albedo modification. And then finally, we'll finish up by discussing the ethical and moral implications of actually performing geoengineering on a large scale. But first up, climate change. All right, so what this figure here shows is the rising surface temperatures across the Earth over the past 100 years. And actually, this is just from the year 2017. Everywhere in red is warmer than average temperatures, all right? And so what you can see is that everywhere on Earth, except for this tiny little bit right off the coast of South America, experienced warmer than average temperatures in the year 2017. In fact, last April was the 400th consecutive month of warmer than average temperatures on Earth. Now, what are the main effects of this? Namely, rising sea levels, all right? So we tend to think of places like Florida and Louisiana as being more prone to sea level rise, but even here in Boston, we're not immune. And so what you can see here, everywhere in dark blue is currently underwater. Everywhere in light blue is what's expected to be lost to the ocean by the end of the century. All right, so it's not very far from now, and my lovely home of MIT is soon to be no more if we don't do something about it. Now, we actually have it relatively well off because there are certain countries that will stop existing. Namely, one of them is the Maldives. It's in the Indian Ocean. It's composed of about 80 islands, and the highest point is really only 3 feet above sea level, which is actually the expected sea level rise globally that we're going to see by the end of the century. And so what this is going to lead to, this is the capital city, by the way, of Male. What this is going to lead to is millions of climate change refugees, as many countries actually cease to exist and millions of people are displaced. So those are a few, impactful reasons to care. I could talk, about climate change for hours and hours and hours, discussing flooding and droughts and agricultural changes, mass starvation, increased extreme weather events like huge hurricane increases. But I don't want to scare you all too much yet. Instead, let's talk about we'll talk about something that politicians care a lot about, which is the extreme cost of dealing with all of these issues, all of these preventable outcomes. And this word preventable is really what I'd like to focus on here. Climate change doesn't need to be as catastrophic if we can do something about it. Now, to prevent these things, the world came together to sign the Paris Agreement in 2015, which was a major step to reduce greenhouse gas emissions, mainly by reducing fossil fuel power generation and replacing it with renewable technologies. And every country in the world, even war-torn Syria, has signed on to this as of last year. The US is actually now the only country in the world not to be a part of this, which in my own personal opinion, I think is a real shame. So why do we care about reducing greenhouse gas emissions? Well, it's the greenhouse effect. And while this is a little bit of a misnomer, I'd like to discuss what the greenhouse effect is, because this is what climate change or what geoengineering is really trying to disrupt. So briefly, the sun emits UV visible and infrared light. Infrared light's also heat light, think of it that way. And it emits it to Earth's surface. A lot of it is just able to pass through the atmosphere completely unhindered and reach Earth's surface. And once it does, the Earth absorbs that light and re-emits it as infrared radiation, heat energy again. And the problem with greenhouse gases, shown as GHG here, is that they are very good at absorbing infrared radiation. They'll absorb some of that and re-emit a good amount back to space, but a lot of it will get sent back down to Earth. And it's this extra bit right here that contributes to the warming that we experience from the greenhouse effect, all right? Now, when we talk about geoengineering, we're going to be talking about disrupting this cycle by reducing the amount of greenhouse gases or by blocking the amount of sunlight that can actually hit Earth's surface. And why do we care about greenhouse gases and the greenhouse effect? It's because the amount of greenhouse gases, namely carbon dioxide, the most important of all the greenhouse gases, correlates very, very well with the average temperature of the atmosphere across the Earth, okay? So this is going back, way back in time, 400,000 years, and shown in blue is carbon dioxide, shown in red is temperature, and you'll see that they follow pretty much the exact same course. The way that we obtain these data is by going to Antarctica and digging up ice cores where tiny bubbles are trapped in the ice cores. Those bubbles were formed, hundreds of thousands of years ago, and using today's technology, we can actually analyze the gas inside those bubbles to both determine the amount of carbon dioxide as well as the temperature of the prehistorical atmosphere. Now, what you can see here is that there is some natural cycle and variability, something that climate change deniers often point out. However, oops, wrong way. However, what we're doing is pushing it way outside the cycle, all right? We are now actually above 400 parts per million. We're climbing way up past 2008's levels. And it's expected that by 2100, if we really start caring as a society, as a world, we might reach 550 parts per million carbon dioxide. It's a concentration unit. But if we don't really care, we don't mitigate our emissions, we're probably going to end up somewhere around 900 parts per million. Think about this. If the temperature tracked pretty well along with this, we're not really sure what's going to happen to our temperature if we don't stop emitting CO2. And so this is actually a very strong word of caution. So, given all of this, what can we actually do about it? Let's talk about geoengineering. This is not a brand new idea. In fact, in 1965, Lyndon Johnson's advisory council suggested that we could deliberately bring about countervailing climate change by raising the reflectivity of the Earth. Essentially, let's reflect more sunlight back out into space, and let's not let as much energy actually reach Earth's surface. All right, so this is 1965. Not really any chance that this would happen. But, keep going the wrong way. In 2005, Paul Crutzen, a Nobel laureate for his work on the ozone hole, wrote an essay about geoengineering. And the effect of this essay was a massive skyrocket in the interest of research in geoengineering. And in fact, it's continued to grow well beyond 50 research papers published every year. And so he's so famous, actually, that scientists began really researching this earnestly and getting lots of funding towards geoengineering. So now this is something that we need to be concerned with. And the UN was actually concerned with this. And in 2010, they passed the Convention on Biological Diversity, preventing geoengineering activities until an adequate scientific basis on which to justify those activities was established. And once again, what you'll notice, surprise, surprise, the US is the only country in the world that has not signed on to this agreement, not ratified this agreement. So, first geoengineering solution we'll talk about, carbon capture and sequestration, hereon referred to as CCS, both to save my words and also for your convenience. So CCS is also known as clean coal in some circles. And what it involves is the direct capture of carbon dioxide emissions from power plant smokestacks and capturing the CO2 and putting it somewhere else, like deep underground in these depleted oil reservoirs or deep underwater in aquifers, all right? And so this is actually a fairly safe idea, okay? We're going to get more, as the talk goes on, we'll get into more and more perhaps catastrophic scenarios. But the main problem with CCS right now is actually its cost. It is far too expensive to actually be employed anywhere in the world. But in the coming years, it's very likely that we'll be able to see more and more CCS operations. Now, one of the dangers that we think about with CCS is what happens if the CO2 that we put underground escapes, okay? And for this, we're going to turn to the natural example of Lake Nyos in Cameroon. Lake Nyos is a volcanic crater lake, and it's actually very deep and narrow, okay? At the bottom of this lake, there are volcanic vents which CO2 bubbles through, and the CO2 gets sequestered at the bottom of the lake due to temperature gradients and lots of water pressure at the bottom. But, as happened several decades ago, an earthquake or rock slide, it's unclear, it triggered a massive turnover of the water, all right? So the water at the bottom started bubbling up, the CO2 started bubbling up to the surface, and once it did, it erupted in what's called a limnic eruption, and the CO2 flowed out of the volcano, and because CO2 is more dense than air, it hugged the ground, and 1,800 people were killed, and 3,500 livestock were all suffocated. And this was in a very rural area, a very lightly populated area, and still the casualties were huge. So imagine now if this were performed in an urban area where power plants exist, the casualties could be far greater. And this is a real danger that is preventing a lot of communities from adopting CCS. Now, another form of CCS is ocean fertilization. So instead of taking carbon dioxide from power plants, let's just try to turn nature into a better carbon sink. And the way that people want to do this is by increasing phytoplankton blooms. So phytoplankton are microscopic organisms, and they bloom in huge quantities, like this one off the coast of Norway. The problem is that they require lots of nutrients to grow. And so the idea is, can we make more marine phytoplankton to uptake more CO2? And the way that people are thinking about doing this, and the way that has actually been done in potential violation of international law, I should say, according to that UN treaty, is by dumping iron filings into the ocean. Iron is a limiting nutrient for phytoplankton growth, and so by dumping lots of iron into the ocean, we may be able to stimulate their growth and thus stimulate the uptake of CO2 via photosynthesis. And lo and behold, in 2012, when this was actually performed off the coast of Canada, it looks like it worked. This orange blob here is a satellite image showing really high chlorophyll concentrations, implying very high phytoplankton concentrations in the area. And it seems to have actually been a success and actually significantly increased CO2 consumption as well. Now, while this is a good sign, there is a huge danger to this, which is that it could actually disrupt the entire global food web. Shocker, right? So the way that this works is by creating dead zones. And when you have high nutrient input, like the high iron input that we would put in for ocean fertilization, you get huge blooms of algae or phytoplankton that as they die, they sink and get decomposed by bacteria who eat up all of the oxygen in the water, making it impossible for fish and crustaceans and plants to have any oxygen to survive. And so what you end up with is, instead of these lovely happy fish, you end up with areas of incredibly low life, essentially only bacteria. And this is not just an abstract risk, this is actually a huge problem right now in the Gulf of Mexico from agricultural runoff from the Mississippi Delta. So we are seeing this already, but not because of geoengineering. All right, so I hope that you're sufficiently scared. It's going to get a little scarier now, though. So we're going to talk now about something that's closer to my home in the atmosphere, stratospheric aerosol albedo modification, which I am now only going to refer to as SAM, S-A-A-M. All right. So for this, we're going to look at volcanoes for inspiration, all right? Now, volcanoes, such as El Chichon and Mount Pinatubo, when they erupted, El Chichon in Mexico, Mount Pinatubo in the Philippines, there was actually an appreciable decrease in the amount of sunlight that reached Earth's surface. And after Mount Pinatubo, the Earth cooled essentially by 1 degree Fahrenheit on average, which is pretty astounding. And so scientists looked at this and said, what if we tried to emulate a volcano? All right, nothing wrong with that. Let's look at Mount Pinatubo, 1991. This is the eruption that occurred. It was a massive eruption, perhaps one of the most powerful in history, and it threw up 20 million tons of this gas, sulfur dioxide. into the stratosphere, 25 miles up. For reference, most planes only fly about 6 miles in the atmosphere, 6 miles up. So this is something like 5 times higher or 4 times higher than most planes actually fly. And what happened was the gases and the particles that were ejected by this volcano formed kind of a blanket over the entire Earth in the stratosphere in the intervening years. Now, what this blanket did is it scattered sunlight directly back into space. So without this blanket, we would see sunlight, more sunlight reach Earth's surface. With this little blanket of particles, we see a scattering of sunlight back. And by decreasing the amount of sunlight that actually Earth's surface, we weaken the greenhouse effect. Now, it's not difficult to see actually how we could emulate a volcano. The compounds that the volcano ejected are actually commonly found in things like fertilizer and are really cheap, actually. But how we get them into the stratosphere is a much different problem. And so for that, I'd like to play my favorite game, which is let's look at different technology costs and let's compare them to their US budget equivalent to just kind of get a sense of what's happening. I know, I play weird games. So, first, the idea is we're going to start at the bottom and go up. Planes. We already have planes, and we have planes that can fly in the stratosphere. So in order to inject all of the particles that we need to in the stratosphere every year, it would cost about $10 billion, which is double the EPA's spending. All right? $10 billion actually not that much. Pretty easy to do. Hybrid airships like blimps and things, or blimp planes, think of it that way, that would cost about $20 billion, which is NASA's entire budget. All right, what if we build a pipeline, from the ground level, we're just going to build a pipe to the stratosphere. Theoretically possible according to material scientists, so I'm told. That would cost $100 billion a year. That's about 2.5 times Massachusetts' entire state budget. All right, and Massachusetts has a relatively large economy. Now let's look at military options. If we filled artillery shells with these particles and had them explode in the stratosphere and inject their loads, that would be $500 billion a year, which is the entire US military budget. Okay? And now the most outlandish, but also sadly the most effective potential solution is using rockets, and that would cost $20 trillion a year, which is the entire US GDP. All right? So none of these options are particularly cheap, but the ones down here, maybe not the gas pipeline, but the ones down here are certainly feasible to actually implement. But do we want to implement them? All right? This is a problem because once we start geoengineering, we wouldn't be able to stop, okay? Particles fall out of the atmosphere and we need to continually replenish them in order to actually have the geoengineering succeed. So what I'm going to show you here now are model simulations of if we were to start geoengineering in 2008 by injecting different amounts of particles into the stratosphere, okay? And so what the y-axis shows is the temperature anomaly, aka the temperature increase that we've experienced compared to the 1950 to 1980 average temperature. And you can see that the temperatures have been slowly rising, but according to the simulation, once geoengineering begins, looking at the brown and black lines here, which are large amounts of particle injections in tropical stratospheric environments, we would see actual very strong and quick decreases in global temperatures. It appears as though this would work. However, the problem is that once you stop geoengineering and the particles settle out of the atmosphere, that's it. It's going to go back to normal. So you have to keep doing it. You can't stop. So essentially, this is a cost that you're putting on humanity forever. And as we continue to increase greenhouse gas emissions, we are going to need to put more and more particles into the stratosphere. All right? Now, not only that, but these particles lead to ozone destruction. So we've worked very hard to close the ozone hole and to decrease its size. But these particles catalyze ozone destruction reactions, okay? And so the big issue, what the simulations will show is that without particle injections, we still have a little bit of an ozone hole by 2025, but with the injections, the ozone hole is much, much bigger, okay? And another issue, by no means the last issue with this, but at limits of time, I can only talk about so many catastrophic things. This would alter global precipitation patterns likely. Notably, in the Indian monsoon, we would see huge decreases in the amount of rainfall, which could totally disrupt their entire agricultural system, leading to mass starvation, migration, refugee crises, etc. And other parts of the country would also not be immune, or of the world's. Southeast Asia in particular would be very harshly hit. Okay, so that was depressing. So let's turn to something funny that's never going to happen. Space mirrors, last thing I'm going to talk about. Yep, space mirrors. This is a real idea someone has proposed that will never happen. I will bet my entire everything on this. The idea is to inject trillions of little mirrors at this point between the sun and the Earth, and it would kind of create a little shadow across the Earth, all right? The problem is, as the National Academy of Sciences, which is actually only about a mile or so that way, they say, quote, "These ideas require the ability to manufacture in space, making them impractical at the current time," which I believe is the nicest way of saying this is a really dumb idea. Let's never do this. All right, and lastly, very briefly, we'll discuss the ethical and moral implications of doing this. Obviously, some of the benefits are that we would cool the planet. We would likely see reversed ice sheet melting, ice cap melting, reverse sea level rise. There are a bunch of things. This would essentially reverse our unintentional climate change effects. The problem is, when we look at the risks, they are much larger, and in my opinion, the risks far outweigh any of the benefits currently, okay? The biggest risk in my mind is whose hand is on the thermostat, all right? Some of the costs that I'd lined out, like $10 billion, $20 billion a year, those are things that a single government like the US or China could unilaterally impose on the world. They could control the world's climate if we want to. And that's a really scary thought. So controlling the world's climate could be to one nation's benefit over another, and also could actually lead to a militarization of the technology. You could, cut off rain to a country and essentially kill their agriculture. You could starve their people. There are a lot of dangers with researching this that still need to be thought out. But two that are a lot more abstract and that I'll end on are the moral hazard and the moral authority of actually performing geoengineering. Namely, the moral hazard, if this does work, would this stop our drive to reduce greenhouse gas emissions? I think it probably would. There wouldn't be as much of an incentive to overhaul our system. And then lastly, and something that I think everyone needs to think about individually, is do we have the moral authority to do this to the Earth? Is this something that humans can do to influence the entire planet? And that's not something that I can answer. However, to give my closing thoughts on this, I would say that we should avoid geoengineering as much as possible. We should focus on going to renewable technologies, eliminating fossil fuel use by 2050, so that we don't have to encounter any of these potentially catastrophic scenarios. And with that, I thank you, and I'll take any questions. Okay.
Burning question.
Yeah.
I was wondering if we could look at the ozone layer hole
Sure.
as a potential solution or a potential example of where we actually might have solved something. So I wanted to ask you, number one, is the hole in the ozone layer, has that largely been mitigated by now? And because I think that's an example where we did kind of come together and ban CFCs.
Exactly.
To newer technologies that actually affected this.
So, right. So just to reiterate the question was, is the ozone hole something that we can turn to as an example of something that we've largely started to fix, and actually the world has come together by mitigating CFC chlorofluorocarbon emissions? The answer is we have started closing the ozone hole finally. In my opinion, the Montreal Protocol, 1982, I think, is what banned chlorofluorocarbon emissions across the world, is one of the most successful global treaties ever. ever, and it really has stopped the growth and actually started shrinking the ozone hole. The ozone hole reached its maximum size in 2007, but it's been slowly shrinking ever since. And if we were to do this, this would really be, I think, a slap in the face of potentially the world's greatest environmental achievement by reopening the ozone hole. Yeah.
Actually, unfortunately, we don't have time for more questions at this moment, but you are welcome to come talk to the speakers after the session. Also, we have lunch right after this. Will you be around for lunch?
Come eat and talk about climate with me.
Okay, another round of applause.